which is based on the concept of binary lifting to solve the classical uh, like the pth ancestor of a node, this problem. So we've been given a tree and and we've been given a tree and we've been given m queries. In each query we've been given two integers v and p, and we need to find the number of uh, nodes such that are pth cousins of the node v for each query. So the idea for this is, let's say this is our note that first of all the tree need not be connected. So basically what I mean to say by this is, in the family relationship tree, uh, the number of edges might not be n minus 1 because it might be a forest rather than a tree. So for example, in the question, this example is given, which is not a tree, it is a forest. By forest, I mean that the number of components in the graph is greater than 1. So these are two distinct components of the graph. That's why it's a forest and not a tree. So let's say we've been given this this forest, and we've been given in a query, we've been given this as the V node and P is equal to, let's say, 1. So for this particular query the answer would be 1 because this is the pth cousin of node. Also, if considering another example, if P was 2 instead of 1, then the answer would have been this, this and this. So the answer would have been 3 because these are the three pth cousins, three 2th pth cousins where P is equal to 2 of node, this node. Now the way we think about solving the question is, for each query VP, go to the pth parent of V. So for this query, we would go to this parent, the second parent of node, which is this. Let's call this ancestor, and we need to find the number of nodes in the subtree of go to pth parent of V. Let's call this ancestor. We need to find the number of nodes in the subtree of ancestor at a depth equal to depth of V, where V is this node. So the let's call this n. So the answer would be n minus 1. And with the special case that if p if in the query v comma p is less than the depth of node v, then answer would be 0. We'll need to print 0. So yeah, this is the logic of the question. Moving on to the code. Okay, now we need to discuss how to answer the query, that how to find the pth ancestor of a node or the pth parent of node v efficiently. We use binary lifting for this to answer this efficiently in order of log n. Let's see this how it is done in code. So let's discuss what the broad logic of binary lifting is. To find the pth parent of v, first decompose p in its binary form. Let's say this is the binary form. Let's say the binary form of p is this. So we need to first go to the, we'll check whether this bit is on. This bit is on, so go shift to like 1 2 4 8 places. So we shift to 8 places. Let's say this is the 8th place. Then this bit is off, so we need not shift. This bit is on, so we shift 2 places. This bit is on, so shift 1 place. So this is the required parent, and we store, we efficiently move to consecutive parents via storing a DP array. Now let's move to the code where I'll explain in details. And okay, one more thing that needs to be explained is how do we like check the number of nodes in subtree of ancestor uh, at a depth is equal to depth v. So for that we maintain a map where map uh, map of depth stores the series of times, like the sorted vector of times rather, sorted vector of times uh, obtained from DFS. So once we have maintained the structure, to answer the query b comma p, uh, okay, once we have maintained this, we need to we need to find the number of nodes in the subtree. Okay, number of nodes in subtree of ancestor at depth d, let's say. So the answer for this would be lower bound mp of d dot begin dot end and time out of ancestor minus lower bound everything same t in of ancestor. So this basically gives the list of the number of nodes in the subtree of ancestor at depth d. But the problem with this is I'll give double that answer, so we need to divide. So let's say this is required. So required would be number of nodes by 2, and the answer for query would be required minus 1, because for the number of pth cousins, uh, the pth, so basically v won't be included in the number of pth cousins, we need to discount v. So this is minus 1 is to discount v from the list of like pth cousins of v. Yeah, so moving on to the code. This is again what we discussed, depth t in, t out, pair we'll discuss. This is like for if p is equal to 0, we'll not make any edge, rather we'll use it to start a DFS from this node as the root of that particular tree in the whole forest. So this is the DFS. How the DFS looks is we'll push, so for this depth we'll push the timer, t in will store, t out will store, for this particular node depth of this node will store, and pair is, okay, let's define what pair is. Par of node comma I is the ith parent of node, or rather the 2 par ith parent of node. So the recurrence of this is parent of node comma I, parent of node comma I minus 1, okay, is basically the parent of node comma I minus 1, I minus 1, because um, let's say this is node and I is equal to 2, so we need to go from this node to 1 2 3 4 this node. So where node comma 2 in this case would be parent of node comma 1 1. So parent of node comma 1 is uh, parent of node comma 1 is again parent of node comma 0 comma 0, and parent of node comma 0, as we say in the base case here, is just the immediate parent. So parent of node comma 0 is this node. Let's call this 1, let's call this 2, let's call this 3, let's call this 4, let's call this 0, node 0. So parent of node comma 0 is node 1 comma 0, and again by the formula this is 2, so this is, sorry, this n1 node 1, sorry, node 2, and using this would be is equal to parent of node 2 comma 1, which is node 3. Oh, sorry, comma 1 is again nothing but parent of uh, node 2 comma 0 and 0, which is parent of node 3 comma 0, which is node 4. So we see that this formula works because 2 because basically 2 par x can be written as 2 par x minus 1 into 2 par x minus 1. This is the logic that extends to this code. Yeah, sorry, 2 par x minus 1, 2 par x is equal to 2 par x minus 1 plus 2 par x minus 1. This is the logic that extends to this code. Yeah, so again moving on to the code. This is the code, the same formula we discussed. This is DFS, moving on to the neighbors. Once we've done this, if depth is less than p, we need to output 0. Otherwise, find node is basically the ancestor we were talking about. RD is the required depth, and this is the number of this is like the number of nodes times 2 uh, that are present at depth d in the subtree of ancestor, and we need to report this answer. Yeah, so this was a good problem. I read about binary lifting today, and this was a good problem to implement.